So now we can take a step back and try to understand the optimization problem we want to solve with VAE. This problem is recalled here, which is maximizing the elbow as a function of lambda and theta. The elbow can be written as the difference between these two terms. The first term is an expected likelihood. It forces the distribution Q lambda star, the true distribution that maximizes the elbow, to be such that the probability of observing X is large. The second term can be seen as a penalty. It forces the distribution Q lambda star to be close to the prior P theta Z. So the first term corresponds to the maximization of the likelihood. It is a classical term. The second term forces the distribution Q lambda star to be close to the prior we've put on the latent variables. So there is a trade-off between a data-driven term, the first one, and a penalty term, here stated in the form of a KL divergence between the distribution and the prior. Here, there is no global latent variable. Observations x1 until xn are independent, and xi depends only on zi and not on the other latent variables zj. Each latent variable is associated to one observation. Here are some comments on VAE. To use VAE, you need to specify a prior distribution Pz, which is easy to sample from, usually a Gaussian distribution. You also need to specify a conditional likelihood P theta of x given z that must be computable. This is a distribution output by the decoder. Usually, these two distributions are set to be Gaussian or uniform. Finally, here are some benefits from using VAE. The prior on the latent space allows you to inject information in the distribution of z, and you can also estimate the variance or obtain prediction intervals because you have access to the distribution of z. Besides, since you have a prior on the distribution of z, you can use this prior in order to generate new data. Indeed, you can generate z with a Gaussian distribution, then apply the decoder in order to get the distribution of x given z, and finally sample from the distribution. Variational autoencoders can be used to produce data, but there is no closed form expression for the density. So it's a situation in which we have a parametric form for the density because everything in the autoencoder is parametric, but we do not have an explicit parametric form for the density of X.